Here we can see a cart experiment performed with a cart, a magnetic bumper, a mass of 30 grams, and a simple pulley system. We will be using the data collected by the cart sensors in order to estimate the mass of both the cart and the bumper, the mass of the bumper by itself, and then the mass of the cart. The experiment setup can be modeled as follows.
The pulley system can be depicted as shown with lengths XA and XB, representing the vertical and horizontal lengths of rope. We assume the pulley is both frictionless and lightweight.
We can derive the equation XA plus XB equals C for the rope length, as the rope around the pulley itself is constant. By differentiating, we can get an expression for velocity and then again for acceleration.
This can be rearranged to give the magnitude of acceleration at A is equal to the magnitude of acceleration at B, which are our kinematic constraints.
Isolating the cart and the mass individually, we can draw Freebody diagrams to show the forces acting on the objects. Using the equations sum of Fy equals mass 1 times acceleration y and sum of Fx equals mass 2 times acceleration x, we can sum the forces acting on each object and use this to find an expression for the combined mass of the cart.
For the 30-gram mass, we have no horizontal forces, an upwards tension force, and a downwards weight force. This can be rearranged as tension minus mass 1 times gravity is equal to mass times acceleration at A.
For the cart, we have only the tension force in the rope, which can be written as T equals m2 AB.
Finally, we substitute equation 2 into equation 1 by T, the tension force, and rearrange for mass 2. Before we can solve, we need to find a value for acceleration.
From our accelerometer and force sensor data, we can find an average acceleration and force reading for the period between 0.85 seconds and 1.45 seconds. Our average values are 0.925 meters per second squared and 0.0192 newtons for the acceleration and force respectively.
We substitute in an acceleration of 0.925 meters per second squared and obtain a combined mass of 0.2879 kilograms.
In order to find the mass of the bumper, we can use the average force reading of 0.0192 newtons. The force sensor reports the force applied by the bumper onto the cart. Therefore, we can use this to calculate the mass of the bumper.
We rearrange the sum of the forces in the x direction is equal to mass times acceleration in the x direction to get force reading equals to mass of the bumper times by acceleration, and substitute in our values. As the bumper is attached to the cart, they will have the same acceleration of 0.925 meters per second squared. Solving for mass of bumper gives us a mass of 0.0207 kilograms, or 20.7 grams.
Lastly, we will subtract the mass of the bumper from the combined mass to give us the mass of the cart. We calculate this to be mass of cart equals 0.267 kilograms, 267 grams. To summarize, our experiment found a combined mass of 288 grams for both the bumper and the cart, a mass of 20.7 grams for the bumper by itself, and a mass of 267.3 grams for the cart.
The aim of the experiment is to prove the kinematic constraint that acceleration in the x direction is equal to 0 meters per second squared in projectile motion.
A ramp is pinned into place at angles of 20, 30, and 40 degrees above the horizontal on a table that is 71.3 centimeters high.
A small ball, coated in green ink, is then released from the top of the ramp and travels off the table onto the ground, marking its position of landing. The time it takes for the ball to travel from the edge of the table to the landing position is recorded using a stopwatch. This is repeated for all 3 angles on the ramp.
The distance of the landing position from the edge of the table x is then measured using a meter-long ruler. This measurement will be used to compare with the theoretical landing position.
Assuming the horizontal acceleration is 0, a kinematics table illustrating the x motion can be used to calculate the theoretical landing position of the ball in the form of the horizontal distance from the table.
The theoretical value is then compared to the experimental value to prove that the horizontal acceleration equals 0.
Experimental values. At an angle of 20 degrees, this caused an initial velocity of 0.62 meters per second, which caused the ball to travel 31.7 centimeters horizontally. At an angle of 30 degrees, this caused an initial velocity of 0.77 meters per second, and this caused a horizontal distance traveled of 42.7 centimeters. At an angle of 40 degrees, this caused an initial velocity of 0.85 meters per second, and this caused a horizontal distance of 59.1 centimeters.
The motion of a projectile is independent in that the vertical y and horizontal x components can be considered separately.
Therefore, an object in projectile motion can be assumed to have a vertical acceleration equal to the acceleration of the object due to gravity and a horizontal acceleration of 0.
To prove that the horizontal acceleration is a plausible assumption, we set up an experiment to prove that assuming the horizontal acceleration equals 0, the theoretical horizontal displacement of an object in projectile motion x will be the same as the experimental horizontal displacement of the object.
For the first drop, we construct a kinematic conditions table with the information that we have from our experiment. We use this with kinematic equations and assuming constant acceleration in order to determine the horizontal displacement from the edge of the table to where the ball should land in the theoretical scenario. We repeat this again for drop 2. And finally for drop 3.
Our results indicate that the equation ax equals 0 holds true. The experimental horizontal distances we observed in step 3 fall within 1 to 4% of the corresponding theoretical calculations of the angle of release.
Thus, we have evidence to support ax equals 0.
To summarize, we investigated where the horizontal velocity remained constant under projectile motion, hence horizontal acceleration equals 0. Our experimental data confirms this theory, falling within 1 to 4% of theoretical calculations. Therefore, we can assume that under projectile motion, horizontal acceleration is indeed 0.